Morning.
Good morning, Prof.
Hey,
Yeah.
morning.
Maybe we will start at 8:30. Is it okay?
It's nine. Yes, 8:30
8:30.
Eastern time, right?
Oh, yeah, 9:30.
Oh,
Okay,
okay.
okay.
How can we maybe put some information on the board?
Sorry, Prof.
I mean, I will put some information on the electronic board so that the students will know. We postpone it to 9:30.
Yeah, okay.
So how about you, Anisha?
Yeah, I'm fine, Prof.
Good. So today you and the other student will be also the meditator for us.
Yeah,
Yes. Okay. It seems a bit simpler today. We only have 4 lectures. Okay.
yeah, yeah.
So maybe yeah, we won't have any opening today. But if Professor Moody want to say something, that would be just fine. Okay. Before start.
Yeah, yeah. It's okay. It's okay.
Okay. Good. So just let me know when you're ready. Okay.
Yeah, it's okay with me.
Morning, Professor Moody. Moody, how are you?
Good morning, Prof. Chen.
Morning. How are you?
I'm fine.
Good.
Thank
Fine,
you.
but busy, right?
Yeah. Okay.
Thank you for coming again. Yeah.
Yeah. Today, our student will give all of us information about their research.
That'd be good. Yeah. I would like to learn something from them. Yeah.
Okay.
Okay. Yeah. And I myself will talk a little bit about biotechnology used in soil remediation too.
Okay.
Give us some instruction or give us some a question or something. Yeah, please.
Okay. Mhm.
Okay.
Okay. We will wait another couple minutes.
Okay,
Okay.
sure.
Yeah.
So
Professor, is that okay if we start this meeting now?
Sure, let's go ahead. Yeah.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Good morning,
Morning.
everyone.
Morning.
Welcome back to all honorable attendees at collaboration between Universitas Negeri Jakarta and National Council University of Science and Technology on Tuesday, November 21, 2023.
Nice to meet you again, and my name is Anissa.
My name is Gusti Anggisa Putri. We will also be master of ceremony today.
Okay, we will take a photo together at the beginning of this activity, and attendees are invited to turn on the camera. Anybody is who will on the camera?
Hello，大家尽量把那个相机打开吧，他们要照相。
Okay, I will help to count. 3, 2, 1. Okay, once again. 3, 2, 1.
Okay, how about pause? Good.
Oh, okay. Okay, okay. Okay, once again. 3, 2, 1.
Okay,
Okay.
thank you, thank you.
Thank you to everyone who participated in this photo session.
Okay, before we enter the learning material session, we will introduce our amazing speaker today. Presentation, Jefferson Declan SSI and Tiara Fahriza. So I will
Okay, I will remember all of you guys to first our speaker today is Professor Shitian Chen, our head of Department of Safety, Health and Environmental Engineering and head of Agro-Environmental Testing and Inspection Center. And his research areas are soil or water remediation, biotechnology, catalytic oxidation, statistic modeling, agro-waste, recycling, and reuse. And he has selected publication recently. And for the last but not least, he also got many achieved in the academic field. Okay, the next speaker.
So let me introduce our second speaker, that is Jefferson Limport Declan SSI, or common called Declan. He is a fresh graduate of chemistry and research assistant of UI Pendeteksi Bakteri Pathogen, and his focus research area is about biotechnology. He has many experience, such as become internship and staff of Lamsama, lecture assistant of bioscience course, and lecture assistant of biotechnology course. So he also has several research publications and conference presentations, as you can see on the screen. So let's introduce our third speaker.
Okay, the next speaker is Meng Wei Jian, or also we know as Jasonson. He is a PhD candidate at NKUST. His focused research area is about soil and groundwater remediation, and he has many experiences. He also has several research publication and conferences presentations, as you can see on the screen.
And the last one is our fourth speaker, Tiara Fahriza. She is an undergraduate chemistry student at Universitas Negeri Jakarta. She is interested in food science, biotechnology, microbiology, and chemistry research. And now she is a research engineer at Pusat Pengumpulan Iptek Pendeteksi Bakteri Pathogen or Detection of Pathogenic Bacteria. She also has several research publications and conference presentations, as you can see on the screen.
Okay, no need to linger any longer. Let us welcome our first speaker today, Professor Shi Tianchen. He will bring the topic about soil biotechnology for toxin removal. So, Prof, this screen is yours.
Okay, thank you. Does everyone hear me okay?
Yeah, it is okay, Prof.
Okay, I try to share the file first. Okay, is that screen okay?
Yeah, that's okay.
Okay, so thank you everyone, and nice to have you all come back here today. It's very tough, actually. It's a kind of challenge to talk in English. It's a non-native language in the early morning. Okay, I will do my best. Hopefully you will enjoy my talk. Today, what I'm trying to talk about is biotechnology used for soil toxin removal. Actually, I'm environmental engineering, so pretty much work is related to removal of pollutants from out of our environment. Here, when I say about biotechnology, I mentioned about using the microbial to degrade the toxin. And then we use some kind of molecular biology technique to monitor the bacteria diversity or microbial diversity in the treatment system. I think this part is more related to Professor Murthy's group. So that's why I prepare this kind of talk today. Okay, as our lovely hosts has introduced, my name is Shitian Chen. I'm now a professor and the head of the Department of Safety, Health, and Environmental Engineering, also Agro-Environment Testing and Inspection Center in the National Kaohsiung University of Science and Technology in Kaohsiung City, Taiwan. So what's the problem? Okay, the problem is about the soil, okay? But I think I will have a couple more slides to talk about where the soil come from and why they got polluted. Okay, so this is actually the structure of our Earth. Okay, if you can look at the top, it's the atmosphere layers. Okay, and then down beneath is the soil layer. Okay, and the most important thing I want to talk about today is the center of the Earth. It's a very hot place because of the heat. Actually, it keeps the convection of the material in the center, and then this heat also move the Earth's floor. Okay, and the movement of the Earth's floor on the Earth's crust actually result in, I think everybody knows, the earthquake. Okay, so here is the kind of a summarized the earthquake incident over about 10-year period. Okay, and then the yellow line means the tectonic plates. Okay, on our crust. Okay, the Earth's crust. So during the movement of those plates, actually they kind of squeeze each other. Okay, and then now the earthquake happened, and the red dots means the one red dot means the extent of one earthquake has a Richter scale greater than 5. Okay, and as you can see that the plate, okay, the borderline of the plate is usually what the earthquake happens often. And I think that the both of us, okay, in Indonesia and Taiwan know this well. Okay, I think in Taiwan we have an earthquake quite frequently, and you can see that's the place of Taiwan in the upper left. Okay, and also Japan and also I think Indonesia. Okay, but in a very stable plate like the United States, you can see no earthquake at all, or seldom you have earthquake. Okay, at all. So what happened to the earthquake? They lift our Earth's crust. That's the problem. Okay, and then when the crust is lifted, firstly there are a lot of mineral rocks. Okay, but over time, because of the weathering and the bioactivity, actually combined with the mineral and the organic part, and we form soil. So actually soil, the formation of soil is a very delicate process. It takes a long time. Okay, they have research shows that in general, we can form a 2.5 centimeter layer of soil if we wait 800 to 1,000 years old, 800 to 1,000 years. Okay, so it's a long time. And then actually, if you go outside right now and we dig the soil, we can easily find more than 1 meter depth of soil. That takes many years to have those kind of soil. So soil actually is a variable source for us. But it's easy to get contaminated because of our activity. Okay, I will show you some polluted soil case later. But as environmental engineering, when we're talking about the pollutant, when the soil is contaminated with some substance we don't want, then we have to do something. And currently, we have two kinds of substance. Actually, they can actually harm us through the contact of those material. One is the heavy metals, okay, like the chromium, the lead, the mercury, cadmium, a lot of heavy metals. Actually, they can have certain kind of interferences in our body metabolism. And the other kind of material which is toxic to our body, I want to talk about today, is the organic toxin. Okay, a lot of organic toxin actually is present in our environment, and they are very diverse format. Some will be in the air, some in the soil, and some even under the soil. So the organic toxin actually is really a problem nowadays in the soil. So if we have that kind of pollution in soil, we have to do something about it. Okay, so our group actually working on soil remediation for quite a long time. So the chart here is show you that once a soil is contaminated, we have a lot of technology that we can clean the soil up. Okay, and then my expertise in this field is we using a chemical oxidation method and then combined with the microbial method. Okay, and we also working on something using the beetle larva to consume the soil with the organic pollutant, and the larva will digest those pollutants in their belly, that's in their intestine. Okay, so a lot of research our laboratory is working on, but today, because of time limitation, I want to talk about a technology that we really want to know more. We call it a two-stage treatment. Is that we treat the soil using chemical oxidation followed by the microbial oxidation or a microbial degradation of that pollutants. Okay, so the pollutants actually we talking about is quite a lot, but I name one for your references because I know in Indonesia you have a lot of petroleum or crude oil production. Okay, and then a very important industry is that naphtha cracking. That means we take the oil, the bigger molecule, and then cracking it down to a small molecule, and then we use those small molecules to make plastic. And here I kind of give you a flowchart of those material during this petrochemical process. Okay, a lot of these chemicals actually in this process is produced in a great amount in our environment, and we use it a lot. And then for the light chemical, like the ethylene, propane, benzene, toluene, xylene, those are toxic, and some are carcinogenic substance. And for the end product, something like a nylon, polyester, PVC pipe, etc., they are the plastic products. Actually, we have those products almost around us everywhere on Earth nowadays. So we do have a problem about using petroleum chemicals. Okay, so the pollution, that's one of pollution I mentioned when the soil gets polluted. And I will also give you an example. We have a particular kinds of pollution in soil come from industry. Okay, this is a real case in the United States. It's we call it a PCP contaminated lumber side pentachlorophenol. PCP means pentachlorophenol. It's a chemical. Actually, it's a pesticide. They can kill most of the pesticides. So why we have this kind of contamination is that when people cut the tree, the big tree, and then they have to preserve the tree from termite or other insects to degrade the tree they collect. So what they do is they kind of coating a pentachlorophenol layer outside the log, the tree they cut out. Okay, and then so the particular layer is toxic to the bugs, but it also toxic to us too. I will explain to you later how they have a toxicity to us, human as well. Okay, so this is kind of a long story. This is the site in the Wisconsin state of the United States. Okay, and it has been contaminated for long. Actually, the site is producing the big log for long from 1953 to 1992. And then because that people kind of reported that they had some kind of pentachlorophenol contamination on this particular site. So that owner actually is kind of abandoned the site. So I actually have a chance to work with the government, and then we kind of to see how can we deal with this kind of soil. So this is the actual top view of the site. The site is actually quite huge. Okay, it's about 850 hectares in size. Okay, so it's a big contamination. We're talking about soil, and then also you have to spend a lot of money, okay, to clean up the site using biological treatment method, which is considered the cheapest expense for this site cleanup. And it takes a long time. We expect it takes more than 20 years to treat this, to remediate this site. Actually, the site is still under remediation, okay? So that's the operation of the site. First, they will collect the topsoil because they have a high content of pentachlorophenol and other kinds of phenol and some PAH. I will introduce that chemical later. So they will collect the top layer of soil and then put them together and then cover it with a plastic cover here. Okay, so this is kind of a standard operation at a time. Okay, so the soil actually is contaminated with a high PCB content in that kind of soil, and then this is the site after the soil excavation. Okay, the top layer is gonna kind of took out, and then on the top you can see because of the toxicity, actually the plant or even the insects, they are very minimal. We don't really see much insect, and then very growth or a nice growth of the plants as well. So this is actually contaminated site we want to treat. So in that particular soil contaminated site, we saw three contaminants. Mainly, one is pentachlorophenol, and one is naphthalene, and one is phenanthrene. Okay, so naphthalene and phenanthrene, we call it PAHs. Okay, so in a laboratory, we want to try to know that if we can degrade those very high concentration pentachlorophenol and PAHs using the bacteria. Okay, but actually we failed to do that. But this is the property of these three chemicals. And then interesting property is the two down beneath. One is the solubility. Actually, it's very low. Okay, the solubility is kind of very small, and only for pentachlorophenol, 14 milligram per liter. And then for the phenanthrene, it's about 1 milligram per liter. That means they won't dissolve in water. Once they combine with the soil, they will stick with the soil. When they stick with the soil, because of the toxicity, the soil will be kind of just dead physically. You can mention that because no insect or maybe a very limited bacteria will grow in that kind of soil. And also they have that's the high toxicity part. Okay, they have LD 50 dose, about 2.3 for rates, and then about 1,000 PAHs also for rates. So those material, they are stick with soil and they are toxic. Okay, so this is some information of the PAHs. That's a polycyclic aromatic hydrocarbon. Okay, they are actually a series of compounds like that. That's the most important characteristics is the ring. Okay, the number of the ring hydrocarbons. Okay, and then they have a higher molecular weight, and then if the molecular weight is higher for the PAHs, their KOW will increase and their toxicity will increase too. They have one very famous compound called benzoyl A-pyrene. This is a carcinogenic material. Okay, so that's why we don't really like to have a PAHs around in our environment. Also, they appear in many places. Okay, like the tobacco smoke, or you have a smoked food. They will generate certain kinds of PAHs, but for a great amount, appearances of the PAHs come from the automobile exhaustion, and then or use of motor oil and asphalt. Okay, so actually this material is just nearby us. So this is very easy. We get some dose from our environment. Okay, and this is the pentachlorophenol. Actually, that substance is forbidden for use, but they still use for the wood protection. Okay, because they are easy to use and cheap. But this material actually is kind of very, what can I say? It's very troublesome material because they are fat soluble. Means that if your hand touch this kind of substance, because they are fat soluble chemicals, that pentachlorophenol will penetrate into your skin directly, and that means that you will receive the dosage from the environment, not through the oral injection, but through your skin. Okay, so the toxicity of pentachlorophenol, as I mentioned, this is for bacteria. Actually, the way they kill bacteria is very unique. Okay, and I have to explain a little bit about biology, that the bacteria actually use glucose, okay, and then to produce some kind of electron and accumulate the electron inside the inner membrane, okay, and then in the outer membrane, because of electron balance, they have a positive charge on the outside membrane of that bacteria, and because of the electron potential, actually they have another molecule called ATPase. That's the enzyme. They will kind of mix the positive and negative electron together and form energy to transfer ADP plus another phosphate to form ATP. That's why the bacteria produce ATP. That's the energy molecule for this bacteria. Okay, so if everything goes fine, the bacteria will produce ATP, that's energy, and the bacteria can kind of swim around the environment and live happily. But when PCP appears, you can see that the PCP will form some kind of bridge around the membrane. So this electron potential will disappear. And once this electron potential disappears, the bacteria won't be able to produce ATP. So the bacteria won't be able to survive. But unfortunately, the human, we have some organelle like this bacteria. We call it mitochondria. Mitochondria has the same kind of reaction. We have electron potential inside the mitochondria, and we use the mitochondria to produce ATP. But when the PCP present, then our mitochondria, just like the bacteria, won't be able to make ATP. So we will use up ATP, and eventually, if you cannot get energy, you will feel weak, and eventually your heart or your brain might just stop. So that's the mechanism of the PCP toxicity. So I will come back a little bit talking about the pollution in the soil. In a wide range of the contaminated site, they always have we call it a hot zone. A hot zone is an area they have a most chemical pollution. Okay, so in this particular site I introduced, they have two kinds of pollutants. One is chlorophenol, including pentachlorophenol, and the other one is PAHs. Okay, different structure of PAH in the soil. Because of the concentration is very high, so that's why we call it hot zone. Sometimes it's very toxic to the bio activity. So the whole site will kind of stop. The material is the toxin, actually, they will remain on the site for a long time. I draw figure to explain what really happened. For example, on the y-axis, if that's the pollutant concentration, okay? If that, sorry about that, if that's a pollutant concentration, actually you can divide this kind of the pollution into three zones, okay? For the first line, at some concentration and up, actually the pollutant could be toxic to the microbes. So the microbe will inhibit it. No degradation will happen. And then in the second zone, if the concentration of the pollutant lower than certain level, the microbial are able to eat them as a food and degrade those chemicals. Okay, but come to the end, they will have another stagnation zone. That means no matter how hard or how long we try to degrade this pollutant out of the soil, they are stay in the soil. Okay, and there are two reasons. One is that we call it that the soil is aged. That means that in the soil particle, the material actually, because they kind of contaminated with the pollutant for a long time, that particular small particle is kind of get inside the soil particle and then difficult to take out. Okay, and then the other reason is that because of the limitation of the microbe to get into the soil particle. So sometimes this pollutant is hard to remove, okay, for a long time. So if we have such the situation like this, okay, so the best strategy to do is that during, if the concentration is higher in certain level, because they are toxic, we cannot use the biotechnology to degrade those toxins. Okay, so we propose to use the oxidation means. Okay, we oxidize the chemical first, and then until that the pollutant come below certain concentration, then we can use the microbial means. Okay, and then we hopefully that if we can do oxidation and microbial treatment, then the pollutant concentration in soil will kind of go down over time. Okay, so that's the strategy for treating this kind of soil. But the question is that the interesting question we want to do this research is that does using an oxidation mean followed by a microbial treatment work? Okay, why we have this kind of doubt? Because the oxidation means upfront we use oxidant and we use some kind of catalyst. We will produce a very strong free radical in this stage. Okay, so this first stage, a lot of free radical actually appeared, and then they are harmful to the microorganisms. Actually, they will destroy certain kinds of organic material in the soil as well. So when we try to revoke the soil and using the bacteria, now that could be a problem. Okay, so we want to know if we're using the oxidation, then followed by the microbial treatment, the system can continue work or not, and if not, why? Okay, so the way we do this research is that we use the two-stage treatment. One is the oxidative reagent. Use the oxidative reagent. One is the using the EDTA ion, okay, and hemming. This is two patent catalysts in our laboratory we have. They can produce a very strong hydroxyl radical and organic radical. And then these two kinds, they produce different kinds of radical. And they are very strong to treat those ring type chemicals, okay? So we add different amount of the catalyst, okay, to different pollutants, okay, and then we add similar amount of the oxygen, that's the peroxide, hydrogen peroxide, to drive this oxidation forward, okay, and then after this oxidation, we actually introduce the bacteria, the known bacteria, two kinds of bacteria, but they are all commonly seen in the soil to try to rejuvenate or to revoke the microbial activity in the soil. And we add some kind of sugar to the soil too to provide substrate. Okay, so that's what we call two-stage treatment with oxidation and with the augmentation of microbes. Okay, but how do we try to know if the bacteria is working properly? Okay, so that's why we adopt a technology called TRFLP, Terminal Restriction Fragment Length Polymorphism technology. Okay, I try to explain a little bit. I think the Indonesian students know more about this technology because you guys doing this all the time. But my student may not learn molecular biology, so I try to explain a little bit. In this technology, they have two ways of doing it. One is RFLP, use PCR, and one is TRFLP, use PCR, then use the sequencer, okay? So the first step is always DNA extraction. We extract the DNA from the soil, and we have the certain gene, that's 16SR DNA, amplified. Okay, then we digest it with the restriction enzyme, certain kinds of restriction enzyme, and then we detect the fragment then, okay? And different bacteria, they will come up with different lengths of fragment. And then they have two kinds of analysis. One, we can use the gel electrophoresis method, and the other, we can use the fragment analysis by sequencer, okay? So the red one is what we did in this research, okay? So I want to explain a little bit more about this technology and then the differences, okay? So we extract DNA from the soil, and we kind of using a certain probe. We use actually two kinds of probe. One is bacterial primer, sorry, not probe. We use two kinds of primers. One is the bacterial primer, one is the archaea primers, because in soil, we could have both microorganisms in the soil, okay? And then after we amplified that certain gene, as a 16SR DNA, then we use the restriction enzyme to cut those 16 rsDNA. So as you can see that different bacteria, they might have different DNA. So we can cut them at different places, okay? And then if you use different restriction enzyme, you can also cut the different, the one show you here, you can also cut the same bacteria with the same kind of 16SR DNA at different places, okay? So by doing so, actually, we can get different lengths of the DNA fragment to represent a different kinds of bacteria, okay? So, but these two primer actually is a little bit different. For the RFLP, the primer the primer contain no fluorescent, okay? But for the sequencer operation, we need a fluorescent primer to do the job, Okay, so a fluorescent primer will allow us to know that how is the length of that the DNA segment after the restriction enzyme treatment. Okay, so for the IFLP and TIFLP, the most important thing is that the final way of making detection. Okay, and if you have a sequencer, that's in the case we do have one, and then we can put everything in a digital numbers. Okay, so that's what we do using this TIFLP technology. Okay, so I think why we select 16SR DNA or RNA as a phylogenetic marker, I think that's quite obvious. Okay, this is a universal protein. I mean, they exist in almost every biolife, bacteria, and microbes, okay, on our Earth. So it's a kind of a, everybody has it, I mean, in terms of microbes. So we use this kind of marker to detect, okay, the primer to amplify this gene, okay, and this under your right hand side is an actual RNA map, okay. So in because the sequence is around 15,000 also, this kind of RNA is curved a certain situation. Okay, so in this one we have to try to identify the suitable primer to amplify this 16SR RNA, and also we have to try different restriction enzyme to see, okay, which one may be better to use. For example, if the restriction enzyme is cutting in certain place in the corner, like that, as in a big angle corner, it's not easy to cut for that restriction enzyme. Okay, so we also try a couple restriction enzyme to see how it works. Okay, so and use TRFLP instead of RFLP because I think they are reproducible technology and they're relatively fast. Okay, in terms of to monitor the microbial diversity, and then they are culture independent. Okay, we don't really the culture is not really have nothing to do with the extraction of DNA and the subsequent operation. So seems pretty nice in that way, and also they can form a digital data instead of just a gel, it's a picture. And we also can link the data to a COM library and to see, to guess actually in this case, what kind of bacteria or archaea is in there. Okay, so the objective here is to monitor the degradation of efficiency of PCP and pH in a two-stage treatment process, as I mentioned, and to conclude the bacteria archaea diversity after the oxidation using the TIFLP analysis. And also, we want to see if we can do better job using the two-stage operation. So we set up 6 soil contaminated with pentachlorophenol and PAHs. Okay, and 1 is controlled without any contaminants. Okay, so basically we analyze the organic content on the PCP and the pH using the GC-FID, and then we analyze the microbial DNA, just use the TRFLP method as I introduced. And here is the primer and the PCR condition we used. Okay, we used 2 primers, one for bacteria, and that's very general design. We didn't do that ourselves. It's a general design we find from the literature, and one is the archaea probe. Okay, and this is the table below is the way we operating the PCR machine. And the restriction enzyme, we actually at first we use 4. Okay, and we test these 4 restriction enzyme, and eventually we see the HAS is 3 is actually has a better result. So we keep using this restriction enzyme to finish the experiment, and that's the dosage of that restriction enzyme we added. Okay, and after that we use that sequencer machine. Okay, it's a Beckman Coulter machine to analyze the length of the DNA cut by the restriction enzyme. So I have a couple of results to show you. That is not the whole result, but this is the 2-stage treatment. So at first, we add the oxidant, the chemicals. Okay, then we wait 2 days, and then we will augment the bacteria and add some sugar to the soil, try to reboot the system. But as you can see here, the oxidation of the chlorophenol is almost it's higher than 90%. Okay, but the PCP is about 93%. But the problem we kind of have is that after the oxidation, there has no degradation of chlorophenol. Even the testing time is more than 3 months. No degradation of pentochlorophenol at all. Okay, and in the control set, we didn't use the oxidation, so the bacteria actually exist in the system, and the degradation is kind of okay over time, but it's very slow, as you can see, that the natural bacteria in the system. But one thing is that pentochlorophenol, because of its toxicity, there has very minimum amount of pentochlorophenol degraded in the system. Okay, so if you look at this table, you can see that the oxidation works, okay, to bring down the chlorophenol concentration. But we expect the bacteria take over and then degrade them all, but it doesn't happen. And then if you look at the one we didn't oxidize the soil, you can see the simpler chlorophenol, like 3-monochlorophenol, 3,5-dichlorophenol, they can be degraded by the bacteria, but the pentochlorophenol, because of their toxicity and their complexity, we don't really see any degradation over time. Okay, so that's actually why we want a 2-stage treatment of the polluted soil, but it doesn't really work out as we want, because as I told you, after the chemical oxidation, there has eventually no degradation of chlorophenol, so whatsoever. Okay, so we take the TRFLP data, as you can see in the control group with the bacteria primer. We can see some fragment, DNA fragment in the control system. Okay, but if we oxidize the system at first, now we see no DNA fragment in the system. So this kind of explains why the system didn't work after the oxidation, because we hardly detect any microbes or bacteria in the oxidation case. Okay, and then for the Archaea primer case, actually in the control, which no oxidation, we can see it's a very diverse system. We have a lot of DNA fragments of the Archaea in the system. Okay, so what I want to see is that one of the fragment means one species of Archaea in our soil. So without oxidation, it's kind of quite a few Archaea in the system. But with the oxidation, you can see the Archaea exists at first. It's kind of fading away. So the oxidation actually harm both the bacteria and the Archaea in our soil system. Okay, but in here we didn't actually mapping the length of the DNA fragment into the DNA database. So we don't have the name of the either bacteria, neither archaea. Okay, and in the PAH case, it's pretty much similar as we saw. Using oxidation, we can oxidize the PAHs. Okay, but that's the indene, netherine, fluorescein, and antherine. This is the, I think, 1 ring, 2 ring, 3 ring, and 4 ring PAHs. The higher of the ring number in the pH, they are more difficult to be oxidized. You can see that in this result. And then it's the same as the pentachlorophenol. We had oxidation, so they got degraded. But after 3 months, no degradation whatsoever, no obvious degradation at all. Okay, but the one without oxidation, we can also see the bacteria degrade certain kinds of pHs, especially the low, the 1 ring and 2 rings pHs. But the higher ring pHs, bacteria cannot degrade them much at all. So same, the TRFOP here, you can see that without degradation, and you can see that the fragment, okay, and then with oxidation, quite minimal actually, both case, okay. But for the archaea, you can see some more diverse archaea in the system and a less diverse system in the soil of archaea with archaea primer. So I think it's kind of simple, but I think that the idea we want to show you got tested. Okay, so we do oxidize the either pentachlorophenol or PAHs at a very high percentage. Okay, more than 70% can be oxidized. But the problem is after we use the oxidant or the oxidation method to treat the soil, the soil is kind of die out. We cannot bring the bacteria activity back to the soil. So that will inhibit the treatment afterwards. So even we wait more than 3 months, the system stopped. No degradation of either PCP or PAHs over time in 3 months, okay? So what we kind of think is that based on the TRFOP result, okay, all the bacteria or archaea diversity is inhibited based on the oxidation, okay? But even they have been oxidized, seems that archaea is more strong than the bacteria species in the soil environment. We see more archaea than bacteria when the soil was oxidized. So what we learned from this experiment is that we find out that if we want the soil kind of if we want to reintroduce the bacteria system back to the oxidized soil, then we need to wait a longer time, because this experiment we only wait 2 days, okay, rather short. And then also we might want to introduce not pure single microbes, but a complex or diverse microbial system with the soil, okay? And then also maybe we want to know what is the highest label the bacteria can degrade the toxin. So if we can use the bacteria early, okay, and then we use less oxidant, that means we don't have to oxidize the soil too much. So they might not be suitable for the bacteria to grow. Actually, in our later experiment, we kind of test these 3 hypotheses, and we extend the soil waiting time to about 10 days. And then the diverse microbial augmentation, we actually augment the soil with some sludge, okay, the food processing sludge. So they have plenty of microbes in there. And then Also, we have determined what is the toxicity label for the pH and PCP in the microbial system. Okay, but we don't have time to show those kind of information. But I think for this particular experiment, we do know the change of microbial diversity versus the TRFLP technology. So that's what I'm present here today. And I know I used too much of time today, but sorry about that. I will get back this screen to the host.
Okay, thank you very much, Professor Shi Tianqian. That's very interesting topic today. And I hope that friends here have a question and can get a lot of
Okay, sure.
knowledge from you, Prof. Yeah.
Okay.
Yeah, and we will also open the discussion session after all speakers today have finished all speakers' presentation.
And now we welcome to our second speaker, Jefferson Liston for Declan SSE. We will talk about the detection of the one of bacteria that cause foodborne disease, Listeria monocytogenes, using the real-time PCR method. So are you ready, Declan?
Yeah, I'm ready.
Okay, thank you. So the screen is yours.
Okay, I will present my PowerPoint. Okay. Can you see my PowerPoint?
Yes.
Okay. I will start this presentation. Before that, I will thank you for all the hosts in this meeting session. And today, my name is Declan, and I'm from the Research Center of Detection for Pathogenic Bacteria, Universitas Negeri Jakarta. And today, I will present about rapid detection of Listeria monocytogenes, targeted ENLA gene in vegetable sample using real-time polymerase chain reaction. The background of our research here is we know that vegetables is one of the food that must consume around the world. And for the Asian, we know that we like to eat the vegetables. And the foodborne disease is occur also at the vegetables in Indonesia. The extraordinary incidence of the foodborne disease reached 128 cases with the effect of 80,000 people became ill. But for around the world, the WHO say that the 600 million cases of foodborne disease occur every year, with 420,000 deaths in 1 year. So the urgency of this research is to make a fast, accurate, sensitive, and specific detection method for microbe, especially on the vegetables, is needed to ensure the food safety. Because one of the agent that can make foodborne disease is a bacteria, and one of the bacteria that can make the foodborne disease is the Listeria monocytogenes. Listeria monocytogenes is a gram-positive bacteria that can lead into the listeriosis with the incubation period between in a range 2 until 70 days, with the symptom that can occur in the human, especially for the non-invasive listeria. We can see at the image in the right is the fever, headache, diarrhea, nausea, and the muscle ache. But for a specific people or high-risk person, such as the pregnant woman, elderly, infant children, and people that have the different ability with their autoimmune, the listeriosis can be invasive with the symptom like meningitis, miscarriage, septicemia, myalgia, and with the death rate until 30%. In the image on the left, that this is the transmission that can happen with the Listeria monocytogenes. Listeria monocytogenes can contaminate the food, and after that, when we eat the food, when we consume the food, the Listeria monocytogenes can enter the human body from the intestine and go into the blood vessels and circulate around the body. Before this research, we already have two detection target of the Listeria monocytogenes that developed in our laboratory. The first is the HLY, and the second is the PRFA gene of the Listeria monocytogenes. The first gene, the HLY gene, is a cholesterol-dependent performing toxin. We use this virulence factor because this virulence factor is one of the ability of the Listeria monocytogenes to escape the phagosomal vacuola and entry the host cytosol. And the second gene that we already use is the PRFA gene. This is the regulate the expression of the listeriosin, is the one of the major toxin that we can see at the Listeria monocytogenes. But in this research, we do the exploration for the more gene that the virulence gene that we can use to detect the Listeria monocytogenes. For this research, we use the ENLA gene. ENLA gene is the internally A protein produced gene that this gene, when we see at the center, the image on the center, the ENL mediated when this protein interact with the receptor in our body, the ecadherin. The ENLA protein can mediate the entry of the Listeria monocytogenes, most of the Listeria monocytogenes into the human body or human cell. So this gene also can we detect around the 90% of the Listeria monocytogenes, especially for the 4C serotype of the Listeria monocytogenes. This is the ENLA gene sequence, and we use the bacteria is strain ATCC 13932, and we use the gene bank to make an in silico analysis of the ENLA gene of the Listeria monocytogenes. In this research, we use real-time PCR. The real-time PCR is the process based on detection of a resulting fluorescence signal that is comparable to the PCR amplification product. And on the right, that this is the three step, the main step of the PCR. The first is denaturating, that when we using the high temperature to make the double strain DNA into the single strain DNA. After we get the single strain DNA, we do the annealing process. This is when the primer attached into the DNA template. After that, we use the extension. And for our research, we use 40 cycle of the real-time PCR to detect the appearances of the Listeria monocytogenes in food or in the bacterial sample. And this is the short film of our genomic project. In Research Center for Detection Pathogenic Bacteria, especially for the genomic project, we divided into the three steps of the research. The first is detection and validation. This is what I do in our laboratory. The second is the effication that later Tiara Fahriza will explain about the effication. And the last is the field study. So in this methodology, I will talk about the detection and the validation of the Listeria monocytogenes. This is the methodology that we use in this research. The first is primer design and the synthesis of the primer. For the primer design, we using the in silico analysis to make a primer and do the optimization or the selection of the primer based on the parameter that we already have from review research. And the second, we grow the Listeria monocytogenes culture, and we do the DNA extraction or the DNA isolation. After we have the DNA, that because this is the first step of our research, that we have to optimization the annealing temperature with using the gradient PCR. After that, we do the real-time PCR optimization. In this process, we divide it into the three steps. The first is the confirmation test. The second is the specificity test, and the last is the sensitivity test. After we have the optimum condition of the real-time PCR, we move into the artificial contamination food detection. This is the primer, the ENLA gene primer that we use to detect Listeria monocytogenes. The primer have 20 base pair, both of the forward and the reverse, with the amplicon that we get is 161 base pair. The parameter for the GC percent, we use 50% for both the primer and from the in silico annealing temperature, we get the temperature for the forward is 55 degrees Celsius and the reverse is 54.8 degrees Celsius. This in silico annealing temperature is needed or important because this is the base on what we choose to make the optimization with the PCR gradient. After that, we growth the DNA, the Listeria monocytogenes, and we do the DNA isolation. The first, we using the brain heart infusion agar to grow the Listeria monocytogenes. On the left, we can see that we have the white colony, white dome colony. That this is the specific color for the Listeria monocytogenes when we cultivate in the agar for the brain heart infusion agar. After that, we take one colony and we do the cultivation in the brain heart infusion broth. And we get the optical density when we incubate for 80 hours with the shaking incubator is around 1.4. After that, we do the DNA isolation and we get to DNA isolate. The first isolate we get is for the purity is 1.9 with the concentration is 150 nanogram per microliter. And for the second isolate, we get with the purity 1.8 with the concentration is 30 nanogram per microliter. This is the quantitative analysis that we use for the DNA is using the nanodrop spectrophotometry. But for the qualitative, the test that we use to validate our isolation, we use the electrophoresis gel agarose that when we see at the well 2 until the well 5, this is the isolate for the Listeria monocytogenes. And the appearance of the band above the 10,000 base pair because the Listeria monocytogenes have a 4 million base pair for whole genome of the DNA bacteria. We can conclude that on this step, we get the DNA isolate for the Listeria monocytogenes. After we do the isolation and we get the DNA, we move into the optimization of the annealing temperature of ENLA gene. And for this step, we use a range of the temperature from 53 degrees Celsius until 62 degrees Celsius with the at the well 1 and the well 15 is a DNA marker of 100 base pair. In this process, the DNLA primer succeeded in amplifying the ENLA gene with the amplicon product length of 161 base pair. And the optimum temperature when we see the electrophoresis result is a range of 55 until the 60 degrees Celsius. This is based on the appearances of the band and also only one band appear when we do the electrophoresis. And but in our research, we choose the temperature of 60 degrees Celsius based on our preview research that this is the best condition or the temperature to do the real-time PCR for detection purpose. And this is also because we want to commercialize our product. So this is the default temperature of the PCR tools is 60 degrees Celsius. And after that, we move into the real-time PCR optimization. And this is the real-time PCR condition that we use. We use 5 steps of the real-time PCR. The first is initial denaturation with 600 seconds in 95 degrees Celsius. After that, we do the denaturation. For the first step in 40 cycle is 15 seconds with the 95 degrees Celsius. After that, we use the annealing at the 60 degrees Celsius for 30 seconds and excision 30 seconds with 72 degrees Celsius, and the last is a final extension in 600 seconds with the 72 degrees Celsius. And this is the first test we use in this optimization for the real-time PCR. The first is the confirmation test of the ENLA primer. For the confirmation test, we get two types of curve. The first on the left is a sigmoid curve, and the right is a melting temperature curve. That for the sigmoid curve, we see that for the Listeria monocytogenes is a blue line, that we get the CT of 11.78 and 11.62 for the Duplo. And this is this 2 CT is make that we already succeed to detect the appearances of the DNA of Listeria monocytogenes from the sample. But when we see in our research, there's appearances of the NTC, because this NTC, the difference between the NTC and the sample is more than 10 cycle, we can conclude that the NTC is a negative. But to validate this data or this result, we do the melting curve analysis. And for the Listeria monocytogenes, the specific melting curve is 80 degrees Celsius. And when we see the NTC, there's a two peak appear and the shifting of the temperature of the melting curve. This is mean that the amplicon produced on the NTC is not the amplicon or the same amplicon with the Listeria monocytogenes sample. So this is can say that the NTC is not contamination, but is more about or because dimer. The second test that we use is the specificity test of the ENLA primer. The specificity test aim to know the capability of the primer to differentiate between the target or the non-target bacteria. And we see that all of the non-target bacteria have a more than 10 cycle from the targeted bacteria. So we can see that this is already negative for all of the non-target bacteria. And when we see also for the TM, for the validate the result of all of the non-target bacteria, there's a shifting. And when we see the melting curve temperature, this is not a one peak appear. So we can differentiate between the sample or the target bacteria and the non-target bacteria. And for the sensitivity test, this is the last test that we use to optimize the real-time PCR method, that we do the serial dilution for the DNA to a range of the DNA concentration. And for the sensitivity test, we get the limit of detection for this primer is 0.01427 nanogram per microliter, or same as 119 CFU per milliliter at the cycle of 26.78. And to validate this data of the sensitivity, we using the standard curve analysis that the parameter of the standard curve analysis, the first for the efficiency of the sensitivity is more than 90%. So that we get in this 1%. So the data that we get in this research already good. The second parameter that we use is the regression, and the regression is already 0.99. And the last, after we do the confirmation test, we do the confirmation test with the contamination food. Why we use artificial contamination food? Because this step is aimed to see the capability of the ENLA gene primer to detect the contamination of the Listeria monocytogenes bacteria in food. So we have to make sure that in our food that we want to detect is already get the bacteria there. So because I used to detect in the vegetables, I use cucumber and lettuce, both on non-dilute and dilute artificial contamination. And for all of the sample, we get that this primer can detect with the cycle at 20 and 23 or 25. The shifting on the cycle that happen in this test is not that we learn is not about the dimer, but it's about the inhibitor. That when we use the literature research for this data, in the lettuce on the cucumber, that we know there is a presence of the inhibitor such as the cellulose that can inhibit the process of the tag polymerase enzyme that we use in the real-time PCR process. This is happen or based on the efficiency that we get is below this 90%. So my suggestion, especially for this test, is we have to maintain how to remove the inhibitor, the food inhibitor, to detect the Listeria monocytogenes using this prime. And this is the conclusion that I get or that we get in this research is the first is the NL gene primer Listeria monocytogenes has been successful in detecting the presence of the Listeria monocytogenes bacterial DNA in lettuce and cucumber using the real-time PCR method. The second, the NL gene primer was able to amplify DNA fragment at CT around 11.74 with the TM value around 80.56 degrees Celsius. The third, that the primer were able to differentiate target bacteria from non-target bacteria based on their CT and the TM value. And the last is the limit of detection value obtained in this research at 119 CFU per milliliter, or same as 0.0427 nanogram per microliter at cycle 26.78. But for the suggestion that I use in this research is this INL primer need to be validated or the validation test in the future, and we have to optimization for the cutoff, because we know that the cutoff is important at the detection method. Thank you for the attention. I giving back into the host.
Okay, thank you very much for the plan. So that's a very interesting topic for us to get to know more about bacterial detection using the real-time.
Okay, after we listen to fascinating research topic on detecting bacteria that cause foodborne disease, now we will listen to a presentation from Jason Shen, the equally outstanding research topic of bioremediation of trichloroethylene contaminated groundwater. And can you hear my voice, Jason Shen?
All right, I just stayed in 1 minute.
Okay. So the screen is yours.
Okay, I just want to make sure everybody can hear me clearly. Hello? Can everybody can hear me clearly and the PowerPoint is okay?
Yes.
Okay. So I will start my presentation. Okay. Hello everyone, my name is Jason, and also I'm an engineer from the environmental consultant company in Taiwan. So today I would like to share some case of remediation site from Taiwan and discuss some of the challenges we are currently facing. And today's topic is bioremediation of trichloroethylene contaminated groundwater. I'm presenter Jason again. And then here is my outline, background, methodology, research, and the discussion. First, about the background. This site is an electroplating factory, and they used the TCE for the material surface washing in the past. Then, as regulations changed, they replaced the TCE with 1-bromopropane. Here, I want to share a short story from the CEO of this company. He ever said the government had praised him for using TCE in the past, but was being fined for using TCE now. Isn't it so ironic? Have you ever wondered if one day in the future, 1-bromopropane or the other chemicals would bring the same situation or problem? I believe that's not only his concerns, but ours. Just remember that he's just following government regulations. Okay? But anyway, that's too far off topic. So let's back to the briefing. And about the geological properties, about the geological properties, we can realize that the soil profile of this site is shown in the picture here, and it is roughly stated as follows. 8 depths is backfill, 5 sand, and then still interbedding. And below 8 to 18 meters is continuous clay. The layer means that basically the nipple is hard to penetrate downward. And about the hydrological properties, the groundwater flow is from northeast to southwest, like here, this way. And the hydraulic conductivity is about 10 to the power of -7 meters per second. This number is very, very slow. And lastly, the groundwater level is between 1.3 to 1.9, affected by the rainfall and below the surface. And then take a look at this map of pollution distribution here. From the early investigation, the number shown in the map is the monitor wells. According to this well, apparently we can find that the high pollution is located in here and here. It's right area of this map. And this finding is similar to previous regions where raw material were used. And the pollution is mainly concentrated in well 14 and well M166-01, and the surrounding spreads to surrounding with groundwater flow. However, inherently, this picture is mainly composed of 2 factories. Here, I use a simple frame to separate them. I call the R side on my right-hand side and the left-hand side on my left-hand side. After comparison, we can clearly tell that the pollution is from R side to the L side through hydraulic transmission. This result is also consistent with the groundwater flow direction mentioned earlier. And about the methodology, after the introduction, I will introduce the methodology about this study. And considering that the pollution area is large, it's a large place, and the concentration distribution is not homogeneous. So we try to divide pollution into zones. In short, the division of A, B, and C regions corresponds to high, medium, and low concentration right here. First, we use two-phase extraction, or so-called TP, treatment at high concentrations. Using this method means that we can both treat gas and water pollution at the same time to achieve a rapid reduction of pure phase pollution. And in the medium concentration area, we use pollution control, such as bioreactive walls or permeable reactive PR barriers, or so-called PRB, to avoid the continuous leakage of pollution. Lastly, we use enhanced in situ bioremediation, or so-called EIB, in low concentration areas. With this method, we mainly promote anaerobic biological reactions. We promote the growth of dechlorination bacteria by adding specific substrates. In addition, in order to avoid making the content too lengthy, here is a brief description of the EIB setting only. We set up total 10-inch injection well, and the concentration of the subject is about 0.3%, and the volume is 8 cubic meter per well. Injection weight is gravity flow, and the frequency is about 2 to 4 times per year, according to the analysis result. And the monitoring indicating is regularly measured indicators are as follows, including the VOC, TOC, and basic water parameters, and the biological indicators such as the number of dechlorination bacteria, etc. And the induction is here in the orange one, and the monitor well is the triangle one, just that you know. And about the result. First, we using this well MW-01, taking this as a representative because TP treatment was used before 2018. So 2018 is here. Here we can see the TC concentration before 2018 here. Orange one is mean TCE. Here we can see that the TCE concentration showed a significant up and down. And this means that when the machine is on and off, for example, like this means this point means the machine is on. So that means the pollution is effectively removed. And when the machine off, the pollution will release again and again and again. So at this point, we find the TCE concentration is down for the down to the like 14 ppm. So we try to shut down the TP system and start the EIB. So the EIB started in the October 2017. The pollution TCE concentration has gradually decreased, right? The orange one, and the DCE and the VC have shown an upward trend. So like the green one, CS1 to DCE, initially it's like 20 almost, but after EIB started, the concentration is much more high, and VC is obviously short. So indicating that the biological effect is in progressing in this site. And then in this slide, we present the same result. The difference is that we divide the site into 3 areas, high, medium, and low, to effectively adjust the concentration scale for comparison, because the high concentration is like 60, and the low one is almost 4. So we adjust the scale to comparison. So basically, after the EIB market on the figure here, the TC concentration in the high and the medium areas are significantly reduced from this way, and this way. TCE significantly decreased, and then DCE and the VC significant increase like here. But in contrast, the trend in the low concentration area is not obvious. So we suspected that it is related to its lower initial concentration, because the initial is almost 4 ppm. So it's not very obvious trend. At the same time, we observed other indicators while the biological reaction is in progress. The amount of dihalocarcoides is between 10 to the power of 3 to 6 cells per milliliter. And subgroups is we find the corneal and the Victoria, and the corneal is relatively abundant. According to the reference, the corneal group can degrade TCE to VC, and the Victoria can degrade VC to acetylene. And about the functional genes show that at least TCE-A and VCRA can be observed in OS here, the data. And the BVCA can also be observed in some monitoring wells, like here. And lastly, high concentration acetylene was also detected. Acetylene, like here, and the higher one, this one is about 0.35 milligram per liter. So based on this result of the biological analysis, it is confirmed that the groundwater microorganisms at this site have the ability to degrade the TCE to acetylene. And then after several years of different remediation, the initial pollution, here is initial one, about 80 milligram per liter. And after years TP treatment, the pollution was reduced from 80 to 50 milligram per liter. And then after 2 years, remediation continues treat. The concentration is from 50 to 30 milligram per liter. And next, the EIB treatment was used, and the concentration decreased below 1 milligram per liter. It's such a high decrease. That is in the last picture of 2018. We can see that the pollution has been more sporadic up to now. The TC concentration in the whole site is about 0.05 milligram per liter, which is the control standard in Taiwan. Overall, the remediation situation appears quite successful. However, there are still some challenges that we can be discussed. 80 to 1. Okay, so about discussion. First, our remediation process is too low. Since the EIB treatment is used, the pollution has shown a plateau at the concentration of about 0.1 milligram per liter and reduced and increased again and again, and a rebound was observed. And second, under the EIB treatment, TCE will be degraded into DCE and VC, and VC has a significant accumulation due to the use of anaerobic treatment. Third, pollution continues to spread downstream with groundwater flow, despite the use of pollution controls. However, due to the operation of the factory, the treatment is so limited. And lastly, the pollution here includes copper and nickel in the soil. If common remediation techniques such as soil washing or ISCO are used, the underground environment will be affected. And finally, the future work. About our future work, we want to screen the specific factors. Observing the situation of microorganisms in the underground is not easy. If we can find a simple indicator to know, it will be more helpful for our other cases in the future. So we hope to do so. And here is all I have. Thank you for listening.
Okay, thank you very much, Jason, for your presentation.
And last but not least, we will come to our fourth speaker, Tiara Fariza. She will talk about sampling and verification test of urinary monocytogen master diagnostic detection kit. So, are you here, Tiara?
Yeah.
Okay, thank you. So this time is yours.
Okay, thank you for the moderator for the time. Okay, I will share my presentation first. I'm still disabled for share screen. Maybe host my account still disabled for participants screen sharing.
Is that okay for now?
Okay. Okay, everyone can see my slide.
Yes.
Yes.
Okay. Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. First, I would like to say thank you for Professor Muktiningsih for giving me this opportunity for presented is the sampling of the application test, the ceremony set again, master diagnostic detection kit. Before I started, maybe the moderator already introduced me, but let me introduce myself first. Okay. My name is Tiara Fariza as a representative and part of the Salmonella team 2019. Okay, first, on this occasion, I would like to present our research development about efficacy tests of Professor Muktiningsih research. So this is our detection kit. This kit is was a product from our research team. In the left side is the real-time PCR kit, and in the right side is the PCR gradient set. And if everyone wants to know more about our team or our detection kit, you can visit our website at the www.bacteripathogenunj.com or come to our Instagram at we.pathogenbacteria. Okay, next move on to what the efficacy test. So in this occasion, I would like to share about the research development about Professor Muktiningsih already been carried out in the previous studies. So this efficacy test is the continued research that Kak Declan have been presented before about detection and validation. So the efficacy test in this study is aimed to evaluate the accuracy and effectiveness of the prototype kit in directly detecting suspected contaminated sample. In this study, identified and differences using the three different methods, such as conventional culture, PCR, and the real-time PCR method for detecting bacteria that may contaminating the food samples. So maybe Professor Muktiningsih already shared about the focus of our research in developing prototype detection kit for detecting foodborne pathogen. And this research, we already have two different prototype kit for the real time and the PCR. We still preparing another prototype kit, and we are making a cooperation with the several company to release the prototype detection kit. And this task is for the efficacy, the prototype detection kit before we release it to the publics. So several methods have been developed to identify pathogenic bacteria in addition of conventional culture, polymerization reaction, or PCR, and have been widely used. So this is today I want to share more about suspected contaminated food sample with the Listeria monocytogen. And while Listeria monocytogen can contaminate food, so Listeria monocytogen is the main bacteria causing listeriosis in humans. And Hello?
Yeah, it's clear. Yes.
Okay, already clear. Okay, maybe I repeat it again from previous slide. Okay. It's clear now? My voice? Okay, okay. I'm sorry, I'm not noticing it. Okay, I will re-present it again. So today I will present to you about the sampling and efficacy test of Listeria monocytogen master diagnostic detection kit. So before I started, I would like to share about our detection kit. So maybe Professor Muktinitsi already present about it, about the research development, and we have the detection kit. In the left side is the real-time PCR kit, and in the right side is the PCR gradient kit. And if everyone wants to know more about our detection kit, or maybe our team of the PUI pendeteksi bakteri patogen, you can visit our website at www.puibakteripatogenunj.com, or maybe can scan the little barcode in the right side is for the website. So today I want to share and talk more about the efficacy test. So maybe Professor Muktiningsi already shared about our focus research in developing of the detection kit for detecting foodborne pathogen. And this our research is already have 12 different prototype kit contain the real-time PCR, also the PCR gradient kit. So why we have to do the efficacy test? So the efficacy test in the study is aims to evaluate the accuracy and the effectiveness of the prototype kit in directly detecting suspected contaminated food sample. So before we release the prototype detection kit for the publics, we have to do the efficacy test first to detect the contaminated food on contaminated food samples directly. So in this study, we identified 3 different methods using a conventional culture, PCR, and the real-time PCR methods in detecting bacteria that may contaminating the food sample directly. So several methods have been developed to identify pathogenic bacteria, as Kak Declan have present before about detecting and validation about the prototype detection kit. In this study, I will talk more about the Listeria monocytogen suspected bacteria on food sample, and we test the efficacy of that bacteria. So Listeria monocytogen is the main bacteria can causing the listeriosis in humans. And the food samples, we can easily find this bacteria in lamb, beef, pork, chicken, fishery products, vegetable, and also in the ready-to-eat foods, such as sausage, nugget, and also meatballs. These bacteria have ability to live in this condition of the high osmotic pressure. So this bacteria can grow well in the food, especially food that have been processed with the added salt. And mainly focused that one of the virulence factor that can make us sick because of the Listeria monocytogen is the HLY gene, is the gene of the responsible for encoding listeriocin or LLO, the pore forming portion that can make us sick and causing listeriosis. So as I can say before, that this efficacy test contain 3 different methods. First is the culture conventional method. Before we do the culture, we do a sampling technique. This is a swab technique on the food surface on the food sample for the culture conventional method. So first, we took one of the nugget samples that we buy from the randomly market. We do a zigzag pattern swab technique for sampling that we can take a possible bacteria may grow on the surface of the food sample and taken out with the cotton bud sterile. After that, the cotton bud sterile or after the swabbing on the several parts of the food surfaces, we culture it on the selective media agar. For this research for detecting the Listeria monocytogen are using the selective media agar of the Listeria selective agar Oxford agar. And after we culture it, we incubate the culture of the selective media overnight at 37 degrees Celsius. After that, this is the result of the culture method in the right side. You can see the difference of the colors of the selective media. So why the media can change or can turn colors to different colors. So the Listeria selective Oxford agar base is a selective medium for the isolation and detection of Listeria monocytogen from food and the environmental samples. So if the culture of the food sample contain the Listeria monocytogen, the media can turn out from the yellowish media into the black zone media agar. So Listeria monocytogen can hydrolyzes the media nutrition of media. It's called acetylene. So the Listeria monocytogen can hydrolyze the acetylene and producing the black zone around the colonies of the gram positive bacteria and inhibit the another gram-negative bacteria. So we can see if this culture media turns out have a small gray bacteria and turn the media into the black zone, the conclusion is the food sample is positive from the Listeria monocytogen. So we can confirm from the first method, this food sample is contain a Listeria monocytogen. Okay. The next part is we do another sampling technique. We do another swab technique for the NA isolation. So same as before, same as the previous, this exact swab technique are used for sampling the possible bacteria may grow on the first sample with the cotton bud cereals. After that, the cotton bud is hydrated with the sodium chloride 0.85% as a rinsing solution to release the possible microorganism and food sample to the suspension. After that, we take out the 200 microliters of the suspension or the rinsing solution and isolated it with genomic DNA kit food protocols. And after that, we do characterization on with the qualitative and the quantitative characterization. The qualitative one is to know about the purity and the concentration of the DNA isolation. Also, the qualitative characterization we do is for know about the how many the base pair of this DNA isolation. After that, we do the PCR methods. So, polymerization reaction method is a technique in molecular biology to use, amplify or multiply a single copy of a piece of DNA. So, this is a result of PCR method using the electrophoresis agar gel with 2% concentration of agar. So, in the first 2 and 3 wells, and the first well is the DNA ladder, so we can know what the best pair of our samples. And 2 and 3 wells is control negative, and the 4th and the 5th well, you can see the band of the DNA amplified at 158 base pair is the control positive. So in this study, we use 2 different control positive. The first one is the Listeria monocytogen pure culture. Also, the food sample artificially contaminated with Listeria monocytogen. The food sample I'm using in this study is the nugget samples, is the food processed samples. And you can see in the well 6 is that an template for the nugget sample. Maybe it's not clear enough to see the band of the food sample, but if we can see more, this is a thin band of amplification at the 158 base pair. compared to the positive control, we can say this DNA of the food sample is amplified with the specific gene that we use in this study is HLY gene. And the conclusion of this result is the food sample is positive from Listeria monocytogenes. And from two methods that we already use, we can say the food sample is contaminated with the Listeria monocytogenes. And next part, for making sure, for detecting the food samples are contaminated with Listeria monocytogenes, we use a real-time PCR method. So as we know, the real-time PCR method is one of the accurate, specific, sensitive method that we can use for detecting a food sample, samples that are contaminated with the bacteria. So this is first one is the CT curve of the food samples, also the positive control that we use. Also, this is the melting curve of the food sample. So in this study, we can see the CT curve of the food sample is presented by this orange line. So if you can see, the nugget 1 have amplified at the cycles 21 until 22 in the duplo treatment, and the NTC or non-temperate control is amplified at 27. As we can see, the DNA template of the food sample is amplified first before the NTC. However, these samples is amplified after the positive control. To make sure the food sample are amplified with the real-time PCR, we see the melting curve of the sample. As we can see in the melting curve, nugget samples have the same peak as a positive control of the pure culture Listeria monocytogenes. Also, the food artificially contaminated with the Listeria monocytogenes. As we can see, these nugget samples have the same peak with the control positive, and we can differentiate with the peak of the no temperate control or NTC. So from the two different things, from the real-time PCR method, we can say the conclusion is the food sample is positive from Listeria monocytogenes. And the conclusion of the three different methods from the culture is a positive, the PCR positive, and the real-time PCR is positive. We can say the samples of the nuggets is positive contaminated with Listeria monocytogenes. As we can see, the real-time PCR method is accurate, more sensitive, specific, and the fastest method that we use for detecting the food sample rather than the PCR, also the culture method that have been more time to get the result of the detecting of the food samples. Okay, maybe that's what I can present to you about my experiences about the efficacy test what I've been working out about for my bachelor thesis. Okay, maybe that's enough for me. I come back the time to the moderator. Thank you.
Thank you so much, Tiara Farisa, for the great presentation topic. And so there will be a question and answer session, and the questioners are invited to use the features to raise hand. So if you wanted to ask, you can raise hand in a feature in the meeting.
Okay, maybe I want to ask first to Prof. Chen. Is that okay, Prof?
Sure. I can hear you.
Yeah, okay. At page 16, you look at birth of bacteria and there are gram-negative and gram-positive bacteria. That's right,
Yes.
bro?
Yes.
So my question, do you use both types of bacteria from gram-positive and gram-negative, or can you use one type of them, maybe just gram-negative or just gram-positive?
Yes, actually we could, but at first in this design, actually we just try to find bacteria is commonly seen in soil because we try to kind of transform or by argument the bacteria into the soil. So we hopefully the bacteria will stay in soil. That's the original intention. Okay, so we don't really pay too much attention about negative and positive bacteria. But as turned out, one is the negative and one is positive, gram-negative and gram-positive bacteria. But we don't really think too much about that design. Yeah, but we can actually using single bacteria. But in the case is that we don't we have limited time for the student to get his her is a lady, her master degree. So we only have one shot. So we use both bacteria in the same system. Does that answer your question?
Okay, so the first bacteria is standby in the soil.
Yeah, both
Is that
bacteria
right?
are commonly seen in the soil. Yes.
Okay. Thank you, bro. Maybe the other question?
Okay. Can I ask a question?
Anybody who asks to our speakers today? Okay.
Can I ask a question? May I? Okay. May I
Yeah,
ask a
sure, bro.
question?
Do you want to ask something?
Yes. For Tiara and for Declan, because you guys seems to do the real-time PCR using to detect the same bacteria, Listeria monocytogenes. But to me, it seems you're using different gene, different primer. Okay, it target a different gene. Okay, so can you explain a little bit maybe why you use different gene? You target a different gene because kind of curious why it's different. And seems to me the difference data is more. Is there any? I mean, what I'm trying to say is any preferences. I mean, you like one primer more than the other.
Maybe I will answer the question. Why we choose more or a new gene for to detect the Listeria monocytogenes? I think when we know that when we do the detection, we have to make sure the detection can the gene can we can appear all of the strain of the Listeria monocytogenes that to validate or to make sure this condition that we make sure not only one gene but yeah the more gene that we use to detect if all of the gene is positive that we we can make sure that what we detect is the Listeria monocytogenes is the first answer that I will give. And the second is for all of the gene is a different position on the genome. So when we know that bacteria can easy or they can get a mutation for the genome, that when we use the more gene and we have we use the different position of this sequence of the gene, that we can minimize that the effect of the mutation when we do detection. And if we see the others real-time PCR kit for the virus or the public bacteria, yeah, I think usually we don't have only one gene, but we can combine two or the three of the gene to detect the Listeria. So maybe Tiara can explain more, because with the three gene that we already have, for now it's all only the HLY that already have the efficacy. But I think for the three of our gene that we have, the three have same potential to be the detection. Maybe Tiara can explain.
Yeah, maybe I will add some answer or from why we use different genes in the study. So mostly we're talking about the prototype detection kit. So when we want to validate the prototype detection kit, we first do the detection as what Kak can do first to know about how the design primer, knowing about the whole genome sequences. And after that, we do the validation. The validation test is meaning to reproduce the method of the genes that we already designed it. That we want to reproduce the method that are not just only one person who can do this method. So everyone can do all the things, we can do all the things, so we can validate it. And after we validate it, we do the application it. So the detecting and the validation it, we not directly tested on the food samples. It's just the artificially contaminated food sample. So the food samples is already artificially contaminated with the specific Listeria monocytogenes, and after that we test it with the specific genes, which is I'm using the HLY, or maybe Kadeklan using the INLA. And after that, we do the efficacy test is to know are the strain or are the specific gene of HLY is already in the food samples directly. So I take out one of the food samples in the random market, and after that I test it directly, not only not doing the artificially contaminated samples, not same as the validation and the detecting. So the detection and validation method I'm using in the efficacy test is for the control positive. And the efficacy test is pure that we, so and the efficacy test basically is, yeah, there's no artificial things in there. So we can I can say there's not only Listeria monocytogen on that food samples. There's many more bacteria maybe growth on that food samples, but I'm just targeting the bacteria of the Listeria monocytogen using the specific gene of the HLY. Maybe that's I can add it more from the efficacy test it is.
Okay. Thank you for the answer. But I think Tikra mentioned a very interesting point that you're talking about if you have to, you can actually put different, maybe 2 kinds or 3 kinds of primer in your real-time PCR, right? So you can actually run the PCR with different gene at a time. So that's kind of interesting. Yeah, that's cool. Okay, thank you for the answer. Yeah. Since you are there, may I ask you another question? Yeah, I have another question for you. Actually, you're talking about, that's very interesting too. You're talking about full inhibition, right? I mean, the full might have some kind of interferences on your primer. Okay. And then your sensitivity might be changed if you're working on the real sample. So I just wondering, do you have any compound or substance that might interfere your precision in terms of using the real-time PCR in a full sample?
Sorry, sir, can you repeat the question because
Sure. I mean, in your very end, you're
Mhm.
talking about the measurement of
Mm.
the real-time PCR result, right? They
Yeah,
might be interfered by
yeah.
some food
Yeah,
inhibitors, something like that. Okay. I don't know if that's the exact words, but
Yeah.
some material actually in the food
Mhm.
might affect the result
Mhm.
of real-time PCR. So I just want to know, do you have any idea what kind of material that might interfere your detection?
For me, that I already searched in the literature review for this problem. Yeah, it's lit or every literature say that this is the inhibitor for the vegetables itself. That we know that the inhibitor in the vegetables is such as cellulose. For my suggestion that I before this I already do this type of washing of the sample. So when we do the isolation of the DNA extraction, we get the centrifuge of our sample, and after we get the pellet of the sample or the bacterial, we wash with the PBS, the phosphate buffer saline, to remove the inhibitor or the every kind from the sample. But after that, I think it's not. Yeah, it's when we talk about the cellulose or other inhibitor, it's there's no significant effect when even if that we already wash the sample. But I think we can get more optimization when we isolate or we extract the DNA from the sample. Maybe for the adding more the proteinase K for the enzyme to cut the protein, or we can use the RNase or everything that can maintain that what we get from the isolation is only the DNA, not the other substance. I think um, uh, maybe for the DNA isolation that we know today is there's many kit that we can use to get the isolate of the DNA, and maybe for now we must to validate that what we get, and we do the more optimization for our kit to isolate the DNA. Maybe it's for me because when I use or I already use to washing the sample, it's not a significant more to remove the inhibitor.
Okay. I have some information. I just wondering if you know that. I think when I doing my first DNA extraction, because we want to avoid some impurity,
Mhm.
actually we use some glass bead, glass bead, and then we can the glass bead. You put in the low temperature, the DNA will attach onto the glass bead, and actually you can isolate the glass bead, and you can throw all the impurity away. Have you this kind of
Yeah,
application?
I have not tried it yet, but maybe it's in the next I will try to because this difficulties is this is the one of our challenge now is to remove the impurities from the DNA.
Yeah, I think to some degree, I think it's important too, because if that will affect the result, that means that might make you misjudge how many bacteria
Yes.
you are looking for in there. So yeah, that's true. That's good. Yeah. Good.
Thank you for the suggestion, Prof.
Thank you.
Okay.
Can I ask some question?
Okay.
Can I ask some
Sorry,
question?
just yeah.
Oh, okay. I just wondering to know if you have any idea, because what I do is about the biological treatment in underground water and the soil. But we all know the biological analysis like qPCR or HOPE we have done. It's really, to be honest, it's really expensive, or that means we have to take a lot of time to do so. So I'm not sure if you all know, we can find a way or find a simple like a kit can use in this site, and we can shorten the time to know. Maybe we don't have to know the real amount of the bacteria, but we can understand the quality, just quality, not real amount. So I'm not sure. Do you have any idea can answer this? Yeah.
For me, that we know that the real-time PCR or the PCR, the conventional PCR, is very expensive. But we know because the real-time PCR have the more expensive with the consumable that we use. But to validate or to detect, I think the real-time PCR is good for now. For the cheap or the cheapest method that we can use, I think we can use the bacterial assay, that the conventional assay. But in our research group, we also do the research about the rapid detections with the antigen antibody. But when we use the antigen antibody analysis, we have to isolate with our body, not in the soil. So we have to different what to say. Today we have two different type of detection. The first, for the genomic is real-time PCR also, but to the second type is the proteomic. We use the rapid antigen antibody. This is the interaction between antigen and antibody from our body. The limitation method also, it's already happened or can implementation in our body, not in the soil or the environment. So because we focus on the field of the food safety and more in the health, I don't. For me, I don't have more information when we using to the soil. But I think if you want to do the evaluation of the bacterial in the soil with the real-time PCR, you can using the more sample, because when we use the more sample for the detection with the real-time PCR, it can low the price when we do the analysis. Maybe it's for me, for Tiara. Can you add something?
Maybe I cannot add it more, because Kadekan already explained it, that we as long we know that the real-time PCR is a kind of the expensive method. Even the instrument is already really highly priced, the consumable, anything that actually that our research team is using the MIQ PCR. So the MIQ PCR is have a specific tube. So maybe in the another real-time PCR, we using the 0.2 milli of the tube. So it's already have it's a general tube that maybe using for the instrument of the real-time PCR. But the MIQ PCR that we use for our research is already have a different tube. So we have buying the tube, buying the consumable, and the real time it is. So it's more highly expensive than using the regular real-time PCR. But the advantage and the good things about MIQ PCR is we didn't have to homogenize the samples and the preparation things. So these instrument is already homogenized it with the principle of the centrifuge. And the advantage of that instrument is we can do the homogenize it without there's things maybe in the result of the homogenize is really applicable for the result of the CT or the TM of the result of the DNA amplified. So maybe I can say that there's no any methods that really cheaper than the real-time PCR, but real-time PCR is already have the best, knowing that it's a more accurate, specific for detecting of the DNA template of bacteria. And for the food samples, maybe of if it can say from the soil, for the environment, maybe we didn't have any things of to give any advice or solution for that. Maybe Kadekan, maybe I can add it more.
The little bit information that we know for the real-time PCR is very fast than others method, because when we use the bacterial culture, we need to wait the incubation 1 days, 2 days, and we get the result. But for the foodborne disease that we face in Indonesia, especially, that 1 day is important because it's when you diarrhea and you get the dehydration, and the ambulation is very dangerous for our body. So what we choose now is not just the price, but the efficiency for the detection. Because in Indonesia, and we know about the COVID, I think every hospital, every health facility already have the PCR. But we know that the real-time PCR is expensive, so we do the more research about the conventional PCR. But the limitation of the conventional PCR unit using the electrophoresis, it's make more time, but it's very short when we compare with another culture method. Maybe it's my answer and the PR.
Okay. Why I asked for this question is because when I met the different professional, I would try to have some interaction and want to know if they have the solution of this question. So anyway, thank you very much for your answer. Thank you.
I think we can discuss more in the next for the I think we in UNJ we also open for the discussion about the others method, because we want to more know about the method that we can use also to make detection of the foodborne disease. I think it's for me.
Yeah, thank you.
Thank you.
Okay, thank you. Are there any question from today's participant? We have the first questioners, Azhar Alfian. Can you hear my voice?
Yes. Is that my voice is clear?
Yeah, that's clear.
Okay. Thank you for the opportunity, and thank you for the lesson, Professor Chen. I want to ask you about system resilience and sustainability. That in your presentation. So my question is, how was the system's resilience to fluctuations in environmental factors evaluated, especially concerning long waiting periods and variations in microbial populations? Are there measures taken to assess the system's ability to recover or adapt to change over time? Thank you.
Okay. Can you hear me? I'm not sure I quite get your question. I think you are asking me about the bacteria number is how can I trace the what kind of bacteria or bacteria number in soil over time or something like that? Can you iterate your question one more time?
Okay. So my question is, how was the system's resilience to fluctuations in environmental factors evaluated, especially concerning long waiting periods and variations in microbial populations? Are there measures taken to assess the system's ability to recover or adapt to change over time?
Okay, and maybe to answer your question, we don't do that. We didn't do that. Okay, at first, in that particular design I present today, is that the story that we wonder, because in our laboratory we are working on oxidation treatment. We use a lot of oxidant, and then we produce a lot of free radical. And we knew at first that those free radicals will kill bacteria. Okay, and some partial information we learned is that after we use that oxidation and we cannot see any further degradation, even we expect the concentration of the pollutant dropped, and that soil is no longer toxic to bacteria, but they won't be able to be degraded over time. Even we put it 3 months. Actually, other people maybe put it even longer. Okay, so we are thinking that something happened after the oxidation. Okay, that's why we use our technology, try to, the TRFLP, try to know the variation of the microbial diversity over time. Okay, and then if you want to say, okay, how many bacteria that I detect can ensure that the soil bioactivity will be rejuvenated or restart in the soil? No, we didn't have the data to tell you that. But only thing we know is that for now is that we know if we want the pollutant to degrade continuously over time, we have to have bacteria in there. Okay, so that's pretty much at that time we did this experiment. So what we did is that we put some pure bacteria into the system and try to see if they are toxic for those bacteria. But actually, I didn't show the data. Actually, all the bacteria we put in were killed. The soil is not suitable to grow bacteria. But pretty much we think that's because of the oxidation. Okay, but sometimes even in without oxidation, we introduce a new bacteria into the soil. They won't be able to survive either. Okay, but to us, I think we know. Anyway, if we look at the TRFLP data, the diversity of the microbial system it's become even no bacteria actually we detect in some cases. Okay, so so I think direct to your answer is no, we don't know how that system can have bioactivity according to the TRFLP data. We can do more if we continue doing this kind of experiment. But for the toxin bioremediation of the pentachlorophenol or the pH, I think to me now, based on the experiment we did, the full bacteria spectrum, okay, instead of just 1 or 2 bacteria, maybe it's more important to let the bacteria activity start again in that kind of soil, I mean the oxidized soil. Actually, in later we do put, as I mentioned, we put the sludge, you know, in the food processing wastewater sludge. They have a lot of bacteria in the soil. Okay, So if we put the sludge with a lot of bacteria, not just one or two bacteria, and mix with the soil, we can see a slow but constant degradation. So what we learned from the study we did is that we will put the oxidized soil and then amend with a lot of bacteria, not just one or two. Okay, so we mix actually half the sludge and half the soil together, and we did see the system will degrade the pentachlorophenol continuously over time again. Okay, so I think that has something to do with the toxicity of the free radical that kill the bacteria. But thank you for your question.
Okay, so thank you for the answer and thank you for the opportunity.
Oh, no problem. If you wanna ask for more questions, if I am not really clear about the answer, you can write down. I can try my best to answer you. Okay.
Yeah, okay, bro. Thank you, Azal, for asking and discussing. Is there any question again? Okay, we also open to friends from NKUST. If you want to ask the questions in Chinese first, it's okay. We are very open.
Well, I just said that sure, you can ask either in Chinese or in Indonesian language. I think we can solve that
Yeah.
kind of problem for you. Okay.
Okay.
But I do have a question for Jason. Just curious, Jason. Based on your experiences, okay, you try two methods. Okay, you try two methods treating the TCE in the groundwater, and I just curious. For example, if you have a site just like the one you worked on, so do you? I mean, how long do you think it takes if you do it? Okay, if you try to clean up the TCE in the groundwater, okay, and the site like your site, how long it take to finish it, to complete the job?
This question is too widely, so I would try to define the question. If we have the TCE site in Taiwan, especially in Taiwan, because sometimes it's combined the soil problem. If we do not have the soil problem, the TCE only in the groundwater, that means it's an easy way to do so. It's like 1 to 2 years if you find a right way, and it can be solved. However, if the pollution into the soil and the groundwater, it's hard to say, but I guess it's maybe about 8 to 10 years, because we don't know how deep the TCE in the soil, and depends on the soil property. If the TCE in the clay soil, it's really hard to treat. So I'm not sure if I answered your question.
Actually, it's quite interesting. That's why I'm asking you, because if we focus on the groundwater TCE contamination, look at your data. Seems if you using the right way, the TCE disappeared quite rapidly, right? Maybe like just like what you say, in 1 or 2 years. But the contamination is always from the top. So
Yeah.
that means the TCE went through the soil and contaminate your groundwater, right?
Yes.
So it seems to me that if you want to remediate a site like that, you have to working on the soil first,
Yes.
all right? Otherwise, if you met the rainfall, then the water, the rain will bring the TCE, and then they will go even deeper and then reach the groundwater. So,
So, okay. Okay, so that's why in my PowerPoint I showed the first, we try to use the TPE, it means the two phase. We can also extract the gas and the liquid both from the underground. So that means we can focus on the pure pollution. So always pure pollution is in the water or some pollution from the soil. So that is what we do first. And after that, we will determine the how much the pollution in the soil. So yes, if the much more pollution in the soil, we have to treat the soil first and then the groundwater. Yeah, that's it. That's what we do.
oh, okay, sounds reasonable. But I just want to update more information about this because, in Taiwan, I think we have many sites contaminated with TCE, right?
Yes.
And then usually a contaminated site, you might have to work or remediate that site for around 6, 7, or even 10 years. Okay, it takes a long time to decontaminate the whole site. So if Jason can do it in 1 or 2 years, he will become a very, very rich man in Taiwan. Okay, so that's a good thing. Well, that's good. But I think that the way you do it, especially talking about EID method, seems that it's very effectively to treat the TCE in the groundwater. That looks nice. Okay, that's good.
Thank
Okay,
you.
thank you, Nen.
Okay, we still open the other question. Is there any question from the participant today? Okay. Shayla? Can you hear my voice?
Okay. Yes. Okay. Thank you for the opportunity for me to speak. First, let me introduce myself. My name is Shayla from Chemistry B 2021. And I want to apologize that I can't turn on my camera because my Wi-Fi is in trouble. First, I want to say thank you for all speakers for today. It's such a wonderful experience. But I still have a question for Ms. Tiara. They're talking about sampling and application test of Listeria monocytogenes master diagnostic detection kit. You said that bacteria can grow in the meat, eggs, sausage, and also chicken nuggets. So my question is, I want to ask more for the sampling methods. On the slide, you said that on sampling test, you used the zigzag sampling for sampling the bacteria from the sample. But I was wondering, is there any other methods for the sampling test? And what if we use another method, not the zigzag instead? And is it the zigzag method is the best method for sampling test? Okay, maybe that's it for my question. Thank you, Ms. Tiara and Kanisa.
Okay. Yes.
Okay, thank you for Sheila for the question. So yeah, I'm using a zigzag swab technique for take the possible bacteria maybe growth on the chicken nuggets or the sausage. So yeah, the sampling technique that I use is there's a lot of sampling technique that may be used for the food samples. Maybe you can search more references because there is a many technique sampling that we can use for the food samples. And I take out the one of the technique sampling is using the swab test. So the swab test is not just only for the zigzag. So the zigzag pattern that I use is just to check the possible contaminated bacteria that may be growth in the food samples. And the zigzag pattern is not just only for the one swab. So do the like 2 or maybe 3 repeated for the zigzag swab. So the bacteria that may be growth on the food sample is can take possible as much. And also the technique sampling is just for the food sample surfaces. So not in the not all the food samples I take it out. So just the food sample surfaces, and every surface of the food sample I take it with the zigzag swab technique, and after that I culture it to the specific selective media agar. And are the zigzag swab technique are the best method? As I can say, and as I can know, it's not the best method, and there's another method that may be really great to take all the possible bacteria maybe growth in the food samples. Why I take it this bacteria? Because my research about the efficacy test is one of the first method that I really use, and is the first method that have been developed of the Professor Mukti. So there's many things that maybe have to research and explore more about the sampling technique, and this one of the easiest sampling technique that may be used for take the possible bacteria that may be growth on the food samples. Maybe it is.
Okay, thank you for the answer, Mrs. Tiara. So you use the zigzag methods because it is the easiest way for the sampling test. Okay, thank you, Mrs. Tiara, for the answer.
Okay, is there any more questions so far? Okay, if the no question, so we are already to the end of the session. Thank you for attending the collectoring between Universitas Negeri Jakarta and National Kaohsiung University of Science and Technology today.
I'm Anissa, and my partner is Gusti as the Master of Ceremony. Today, we want to say goodbye. Thank you very much for all the participants.
We also see you next time and also have a nice day. Wassalamualaikum warahmatullahi wabarakatuh.
Well, I will also want to say thank you for our hosts for these 2 weeks. You've been working very hard and to make this conference very smoothly. And I would like to say thank you to Professor Moody and all the audience. Keep in this lecturing for the until the last minute. Okay, and then thank you very much. And I think this is kind of a very intriguing event, and to learn something from the friend far, far away. I think I personally learned a lot. And if you guys is okay with that, if I think of any question, and when I'm reading your maybe Declan or Tiara or the Professor Moody's PowerPoint, if I have further question, allow me to ask for more. Okay, I think learning something new from you youngster is kind of interesting and very intriguing event for me, and I'm really thankful for you guys giving me this kind of opportunity. Thank you. Very much.
Please share, Professor.
Hey, where's Moti?
Yes, I'm here.
Yeah, you are here to make a closing remark.
Okay. Yeah. Thank you for sharing. Please apologize because I should take care of another problem in my faculty. So thank you again for Prof. Chen and all of the students from Taiwan and Indonesia to contribute for this collaboration session. And this is not this activity, but we can follow to another activity. So we can design another activity to make us join more closely. Okay. Thank you again, and then I wish all of you success and welcome to our campus next time. I will also will come to your campus project.
Oh, okay. You are very welcome. Okay. I will be very happy to see you here. Okay. So see you all then. Bye bye.
Bye.
Thank you, Professor. Thank
Bye.
you.
Bye.
Thank you.